for that. Okay. All right. Okay. So then again, sorry for the delay. Just welcome to today's class on a wonderful Saturday evening, Saturday afternoon. Sorry for that, on 2 p.m. This is teacher Jason here. So some general rules and what we've gone through today, term 1, revision 1. So just a quick recap on the elements to represent. This is an element, not an element, number of elements here. What happens? Two sets are equal if they're exactly the same. The order may be different, henceforth we represent as such. In this case, what happens is P and Q are going to be represented in such a manner. Now, what happens? Empty set, we know it does not have any elements. We can represent it this way. Two names, empty or a null set. And that's why we go to the universal set. We can represent it as C. We call this the universal set. But otherwise, elements not in A, we call it the complement known as A prime. Now, my question is then as such. Can anybody name me an element in the complement of the set? Just throw me a number. What is an element in the set? Right, just throw me a number. What is an element in the set? All right, not in the set, not in the set. All right, Chen Zhen, not inside A. Right, but I think I understand what you meant. So a number not inside A. All right, very good. I believe you got the answer. That's right, Chen Zhen. Anybody else wants to try? Very good, Sophia. Perfect over here. All right, so I believe you got it. 1 and 9 are not in the set, so that's the notion here. So we can actually carry on. 3, 7, 11, 13, 17, 19 are actually not in the set as well. All right, so moving on, what happens is now proper subsets. Over here, how do we classify a proper subset is as accordingly. So because Q over here is the smaller set. So every element of Q, in this case, it's an element of P. But however, what happens is we know to have a proper subset, Q is not equals to P. Henceforth, over here, Q is a proper subset of P. In this case, how we write it again, Q, it's a subset of P without the equal sign. That's what we know as a proper subset. Now, you realize when we talk about subsets, there's two ways. One is a proper subset. The other one is a subset. Now, what is the difference over here? Now, in this case, when we talk about the proper subset, all elements of Y are also elements in X, as we've gone through. And again, the two sets over here, Y is not equals to X. That's what we've gone through before, and we wrote this notion over here. Now, for Z being a subset, we ease the condition a little, if you want to recall. If we talk about a subset, in this case, all elements of Z, in this case, are also elements of X, are also elements of X. Okay, so that's one thing. And in this case, Z and X may be equal. Keyword over here, the word is may be equal. So one thing to take note over here. And the way we write it is this C over here with a below arrow. That's what we indicate as a subset because it can be equal. Now, bringing it up, just two more terminologies before we get on to a particular work example to see how sets apply over here. First one, we talk about the intersection. In this case, when we talk about intersection, we talk about the elements that are common to both sets, M and N. In this case, when we talk about common, we talk about these elements over here, 8 and 16. So that's where when we talk about common, we talk about where they lie in the intersection. And we talk about the intersection, just to recap over here, it's M this way, N, and over here, M, and over here, M intersect N. That's how we write it. It's also known as the set that we are describing. And next up, now, if we talk about union, that means we actually list all the elements which are in M or in N. Hi, Isabel. I hope you are doing good. I hope you can hear me. All right. In this case, we list all the elements over here, 4, 8, 12, 16, 20, 24, 28, and 32. This is what we call the union. And in fact, the union is basically me shading every single element inside over here. It's either M or N or both. This is what we call the union over here. Now, that's where in this case, we write M-U-N, and this is what we call a set. All right, so basically, the first half what we have gone through is just the revision. Now, let's go through a work example. How all these concepts, or in fact, some of them, apply to my work example. So let's look at this. Right now, you realize this particular question is very interesting. In fact, it actually combines one particular concept. So what happens in the sets questions, let's recall, they actually give you the set notation, in fact, how to describe the set. But in this case, your sets are not in just one alphabet, it's two alphabets, and in terms of coordinates. So you realize they write in coordinate form for you over here. Okay, so coordinate form, and this is the description of the sets respectively. This way and this way. Okay, and this is my coordinates. Now to list the elements in A intersect B. Now let's recall. A intersect B, it basically means A and B. So that means my set is actually represented as such. X, Y, and Y minus X is equals to 4. And in this case, X plus 2Y is equals to 5. Now, before I actually solve this, does anybody have some notion of how we actually solve this type of question? What do we actually do? Think about it, just write it down. All right, very good. I think you got the hang of it over there, Chen Chen. There's a particular way we can do it. One of them is what we call the method that you say, which involves a particular concept. Okay, I think you got it. But does anybody else wants to give it a try? Suppose I have these two things over here. What can we do? Let's think about it. Okay, you can list me the method. Okay, I will actually zoom in from there to see whether it is actually sort of correct. Yeah, I'll give you all some time to think about it. Okay, so let's think about it. Okay, I think Chen Chen has got it, but the rest, it's a little bit iffy over here. So let's think about it. Okay, if I want this equation and the other equation to hold, right, what happens is this. Suppose I call this equation 1, I call this equation 2. Okay, what happens if I want this equation and this equation to both be common to each other? In this case, the intersect. That means X and Y have to fall in these two equations. You realize if you were to follow the meaning, I can actually do simultaneous. All right, guys, so that's where you realize I can do simultaneous. One way you can do elimination, or if you want substitution, from 1, you can write Y is equals to X plus 4. This is equals to equation 3. And from here, what you can do, that's where your simultaneous equation comes into play. So that's where you substitute 3 into the equation that is not manipulated, guys. That is not manipulated. So sub 3 into 2, and that's where you have the notion of subbing in. X plus 2, X plus 4 is equals to 5. And from here, it's just going to be a normal algebraic manipulation. So that's where I have X plus 2X plus 8 is equals to 5. All right, just take note from there. And from here, I manipulate 3x is equals to minus 3. And from here, I have x is equals to minus 1. That's the first part of the answer. Now, you realize how I continue on? I need to bring back the equation because I only have x. Y is also another element I need to consider. So what do I need to do? Again, following your simultaneous equation, I need to substitute back to the equation that I have not done yet. So if I were to do it, let me just scroll up a little bit. Sorry for that, for some space. Okay, there we go. Okay, so sub x equals to 1 into the equation. In this case, the easier one to do will be into, I hopefully don't run into myself, equation number 3. So therefore, if you realize, this means my equation y is equals to negative 1 plus 4 because x is minus 1. I'm using this. So this is what I learned in Sec 1. Substitute in, I get the notion of y is equals to 3. So what is my final answer for this? This means that, okay, my final answer is going to be my elements, in this case, A intersect B is only going to contain the element where x is minus 1, y is equals to 3. So that's how I represent it. Okay, so I understand there's a little intersection of a problem here, but that's how I represent it as such. Let me just write it down. Okay, so this is how I solve it. And then if you recall, I just need to combine minus 1 and 3 into my equation over here to form A intersect B as such. All right, I hope you guys got the hang of it. And if you do, what happens is the other notion is going to be the same particular manner. Right, so let me clear some space for you to see the next one. Now, in this case, B intersect C. How is this set going to be defined? Same notion over here. B intersect C is going to be x plus 2y equals to 5. And in this case, you realize this is going to be much more straightforward. I need my solution to fulfill this and this. So what happens? Okay, over here, I have two equations over here. X plus 2y is equals to 5 and x is equals to 3y. Now over here, you can eliminate if you want, but what happens is you can also substitute. Okay, x is equals to 2y. It's already a subject. So what we do, we can do substitute, in this case, 2 into 1. Forming from here, what happens? Okay, substitute 2 equals to into 1. You're going to have immediately 3y plus 2y is equals to, in this case, 5. Forming from there, what happens is we can solve further, simplifying more. So I have 5y is equals to 5, y is equals to 1. From there, you realize I have one of the solutions ready. All I need to do, substitute further. Sub, in this case, therefore, x sub, in this case, y is equals to 1 into one of the simpler equations, in this case number 2, because you need to subtract or do anything else. So y equal into 2, so therefore x is equals to 3 times 1, which is 3. And finally, how do we sort of simplify this? This is equals none other than b intersect c. This is equals to my element, x is 3, y is 1. Right, so what is the moral of the story here? You realize my sets and simultaneous equation questions can sort of come into play. So let me just refresh. This is the first part where I went through over here. Okay, to get my answers. So solving it halfway with my substitution elimination. And the other part is where I actually solve accordingly as well using simultaneous equations. So this is one way whereby set notations can come into play to solve such questions. Interesting, right? So now I hope you guys got the hang of this. Let's see how you guys do it by yourself. Bubble question 1. Let's see how you guys do it. All right. Given the sets, solve them accordingly. Launching the bubble. 1 minute 30 seconds in 3, 2, 1, and let's go. All right. Very good. Okay. So take note of the sets that are used here. All right. Take note of the sets that are used here and solve them accordingly. Okay, you have about 1 minute left. All right, let's see what we have. We have about 1 minute left. Counting down to my last 50, I see where of you all make an error. Take note, I'm doing A intersect B, guys. A intersect B. Take note of what is the set that you are using over here. A and B. Take note, I'm looking at A and B, guys. A and B. Okay, last 30 seconds. A and B, yeah? I'm talking about A and B. Okay, counting down to my last 10. All right, for those who are doing it, heading there. Counting down to my last 4, 3, 2, 1. All right, most of you all got the answer, but let me just go through. Some of you actually made the error of subbing in equation C, but take note, I want equation B because A intersect B. So let's see how it goes by. So I'm not going to write the set notation because when I talk about intersections, it is just notion of solving these two equations over here. So this is equation number 1 and equation number 2. Now, how I will solve this, in this case, you can actually manipulate one of the equations, which in this case, you realize I will manipulate equation number 2. Why number 2? Because from 2, I am gonna have y the subject straight away without involving fractions. And now we know fractions is actually kind of troublesome. We don't want to involve that. So once we have this, we realize, oh, I have manipulated equation 2. I should not use it anymore. Now it's the comparison between 3 and 1. So substitute 3 into 1. So that's where I have 5x minus 2. Over here, 3x minus 4 equals to 6. Now what happens? That's where we continue to simplify further. I'm going to have 5x minus 6x plus 8 is equals to 6. And from here, that's where I simplify much more to give me, in this case, minus x equals to minus 2. Okay, just simplify much more. X is equals to 2. Okay, that's the first part. And from here, I substitute the answers. X is equals to 2 into equation number 3. All right, so that's where I have y is equals to 3 of 2 minus 4. This gives me 2. And henceforth, my answer is 2. Okay, it's not being a tongue twister over here because it is literally x is equals to 2, y is equals to 2, and that's how we represent in a set. Okay, remember your sets must have the weird curly brackets over there to represent them as accordingly. Alright, okay, I hope this is a start because the next one, let's try another one, round 2. Alright, same notion over here, counting down in 3, 2, 1, let's go. Alright, this is gonna be, I would say, much better. Alright, very good, very good, keep it up. This I would say is much better because the substitution here is not that tedious. Okay, let me move this, see the responses. Alright, doing good, perfect. Okay, along the way, let's say you finish a bubble question. If you don't understand any particular part of this particular revision lesson, please feel free to let me know. Okay, take note, this is now A and C, so I'm looking at these two equations here, equation A, equation C. Alright, equation A and equation C. Alright, counting down to my last 40 seconds. Okay. Anyway, this interface, what you have seen over here, and as well as how the bubble questions are laid out, will be how our future SecMath lessons are going to come by. So let us know whether this interface is good or in the long run, if you were to prefer something else. All right, just keep us going and we'll improve ourselves from there. Okay, counting down to my last 14 seconds. Okay, as you will know already, I'll just write down the first step. So 5x minus 2y equals to 6. Y equals to 4x. Okay, how do we solve from here? Counting down, last one, let's see. All right, perfect. Okay, most of you all got it, so let's just do it out for the rest who are unsure. All right. Okay, no worries. Okay, I'm just subbing in accordingly. All right, I'm just roughly gauging the numbers, but good note, you're accurate from there. Okay, so from here, what do we do? You realize 2 is already my subject, so I just substitute. Substitute 2 into my 1. Then from there, what do we do? Okay, so that's where I have 5x minus 2, 4x is equals to 6. And from there, we slowly manipulate. So that's where I have 5x minus 8x is equals to 6. Manipulate further, minus 3x is equals to 6. And from there, what do we do? Okay, from here, we are actually going to just none other than substituting. Not substituting yet, sorry. We are going to simplify further to find my answers for x. So let me just draw a nicer line. Sorry for that. Okay, I'm going to have x is equals to minus 2. And from there, what do I do? Substitute x is equals to minus 2. That's, take note when you divide, okay, certain errors that should not be made. Into, in this case, equation number 2. That's where I have y is equals to 4 times minus 2. This gives me minus 8. And therefore, my set A intersects C, this is going to be minus 2 minus 8. And this is my final answer. So realize this is one interesting sets question that you may face. And of course, there will be more. So stay tuned for that in next week's lesson, all right, where we face more concepts from there. All right, but this is one particular question whereby in terms of sets, it will come out. Okay, now, in terms of sets, let's move on to now. Probability of combined events. So one way whereby probability of combined events can be sort of shown is through a possibility diagram. So what is a possibility diagram? In this case, usually represented in a rectangular grid or table. What happens? We can list all possible outcomes of an experiment, usually if there are 2 simultaneous one of them. So usually 2 of them. Right, so take note, usually 2 possible different outcomes, like 2 events. So what do I mean? So suppose this particular example, I have a fair coin, I toss it up, and a number drawn at random from 1 to 5. So if I have a coin, I toss it up. What are the possible outcomes? So in this case, for the number, you realize there are 5 of them. I'll just label 1, 2, 3, 4, 5. And suppose if there is a coin, if I toss it, it's going to be either heads or tails, right? Only these 2, heads or tails. So that's why I have H and T. And what do we do with the possibility diagram is we actually label all my possible outcomes with this wonderful crosses over here. Okay, so this is an example of a possibility diagram over here as such. Okay, now just give me a moment. Let me just do some erasing. Yes, possibility diagram as such. So this is how I were to do it. Now, let's see what kind of questions that can come up. So, of course, I'm not going to redraw the possibility diagram. Drawn up here for you, printed out nicely over here. So let's see. Find the probability that the number shown is a prime number. Okay, again, this kind of questions, I think I've asked a lot of times, but let's recap. What is my prime number over here that I'm looking at? Type down responses. What is the prime number that I'm looking at? What is my prime number that I'm looking at? Awesome, Chen Zheng. And that's my probability as well. Very good. Does anybody else wants to try? What is my prime number over here? Very, very good, Sophia. Oh, sorry for that. Anybody else wants to try? What is my prime number? Okay, in fact, you realize if you attend my particular lessons, I like to use prime numbers a lot because a lot of people still get strict by prime numbers. But based on your responses, very good. You realize my prime numbers over here are always as such. Not going to change to 3, 5 if these are given. And in this case, the only restriction is numbers. There are no restriction on my coins. So therefore, I circle both over here for heads and tails for 2, 3, and number 5. This gives me total outcomes. You realize 10 crosses, 10 outcomes. In this case, the possible options I'm looking for, it's the circled options. 6 over 10, remember, I don't want to leave it at 6 over 10. We need to simplify. So that's where I simplify, give me 3 over 5. Please remember, if you have a fraction, regardless only numbers or fractions, any common factors, if you can cancel them out in the fraction, please do so. All right, so this is the notion of my prime numbers. Now, with regards to this, over here, I restrict one option, but let's see if I restrict both of them. How will my probability change? Launching my bubble launcher in 3, 2, 1, let's go. Okay, take note, there are now 2 restrictions, coin show tails, and in this case, the number shown is an odd number. All right, so there are now 2 restrictions, which is my answer. All right, very good, but take note, tails and odd number. Tails and odd number, all right? Some of you are falling into the trap. Tails and odd number. I want tails and odd number. What should I have, guys? Okay, so some of the, at the starting, most of you fall into the trap. Take note, now there are 2 events at the same time that are occurring. So how should I do it? Tails and odd numbers. Last 40 seconds. Okay, so tails and odd number. What should I have? Okay, last 20 seconds. So the hints over here, take note, events labeled as such. What are tails? What are my where is my tails? Tails over here, labeled as such, so that's where I have. Odd numbers, what are my odd numbers over here? Counting down to my last 10. Odd numbers, I hope you realize is 1, 3, 5, and I'm looking for the common events that's happening here. Last 4, 3, 2, 1. Okay, at the start there were quite some errors, but don't worry, I'll go through them. At the end, some of you managed to finish it up. That's a good sign. So let's see, tails and number shown, it's an odd number. So let's see. So it's going to be this option, this option, this option. Do not circle the top here because I need tails and odd numbers. Okay, I'm not including heads over here. Okay, I'm not including heads over here. So therefore, what happens is my options, total options 10, I only have 3 possible options. So that's where I have 3 over 10. That is my answer over here as such. All right, just be careful when you're tally with the answers, okay? Some of you actually consider heads. Okay, that's why you'll give me this. Some of you actually sort of consider both even and tails, all right? So different possibilities. So take note from there, see the question, see what is given for you all to solve. All right, now with regards to probability, there are a few ways for which events can be given. So the first one actually links back to your sets. Mutually exclusive events. So let's recap. Mutually exclusive means in this case there are no overlaps, that's one. okay, between two events, no overlaps. We are talking about two events here. Then we are talking about the notion of mutually exclusive. No overlaps. In terms of sets, how do they look like? So this is the notion over here. In terms of sets, if we were to do it this way, suppose I have two sets that are mutually exclusive, that means there is no intersection. So A and B mutually exclusive in such a manner. All right, now with regards to mutually exclusive, there is a particular rule which we can apply. This rule is what we know as your addition rule. So how do we apply? Again, we can go to an example. If they are mutually exclusive, I actually sum both of the probabilities. So example, a probability of a die showing either even number or odd number. It cannot be both because even and odd, they cannot both occur at the same time. So I actually sum them both together. So that's one example. Again, if you don't really understand my description, don't worry. That's where we have a work example to help us out. In this case, a variety of a question. So suppose it is not really clear that this is really mutually exclusive. Let's see. So what does this question say? A spinner with 9 equals number sections as shown here. Again, each time a pointer is spun, is equally likely to stop. So each of them is equally likely. So there's no biasness. So find the probability that it stops on an even number or a multiple of 7. Now, if you were to take a look closely over here, so even number or a multiple of 7. So if we were to do the shading over here, are they mutually exclusive? Over here, because I'm going through, yes, but how do we identify? Again, let's look at the context over here. Very good, Chen Zhe, very fast. Very nice. So over here, even numbers, what do I mean? Even numbers. Okay. Let's go through it for the rest of the benefit, but good job over here, Chen Zheng. Even numbers, what does it mean? Shade it over here. So 2, 2, 4, 2, 8. These are my even numbers. Multiples of 7. That's only one. So, are they mutually exclusive? In this context, yes. Because the spinner is phased as such that even numbers in green and my multiples of 7, there are no intersections. So therefore, doing this, I actually can find the probability 9. If I look the color coding, how many even numbers are there? 5 of them, right? So my probability is 5 over 9 plus 1 over 9 because there's only one multiple of 7. So therefore, this brings us to 6 over 9. And remember to simplify more. This gives me 2 over. In this case, let me just sort of scroll it up 3 for you all to see. Okay, so this should be my final working 2 over 3. So that's how I write it out. Okay, again, mutually exclusive, how to identify? See the events, see whether there are any intersections here. In this case, any two colors sharing one particular option here. Okay, if there's no two colors share particular options, but the colors are separate in the context of this question, they are mutually exclusive. All right, so that's one way. All right, so now, what not to do this? Then, doing a bubble question. So now you realize, this teacher every time like to use prime number, right? But I add it up. Prime number or a perfect square. Launching a bubble launcher in 3, 2, 1, let's go. So prime number or a perfect square. I do hope you all know what is all these terminologies here. Prime number or a perfect square. Alright, but okay, you guys are doing good. Again, label my events here. I want prime number or a perfect square. So what are my prime numbers? What are my perfect square? Okay, again, let me just write a few steps. Okay, so I'm writing prime number, in this case, or perfect square. Alright, very good. Seems like most of you are getting the hang of it, but let's see for the rest. Alright, Dylan, I hope you are doing well because you're telling me that it allows you all to keep your brain cells longer, so I hope you are doing well. Counting down to my last 30, you guys are doing good for this question. It's a very good sign. It's a very good sign. Yes, I know. I saw. So don't worry. So I hope the brain cells are still there. Okay. I hope you are doing good. Okay, counting down to my last 10. All right. Doing good, doing good. All right, counting down to my last 4. I mean, I'm just fast forwarding, so don't worry, Chen Chen. I'm taking note. Last 3, 2, 1. Time's up. All right, awesome job over here. Most of you have managed to conquer this question. But then again, how do we actually do this for those who have yet to answer this accordingly? So prime numbers, perfect square. Again, one of my prime numbers. Okay, prime numbers, take note 1 is not my prime. Or in this case, there's no 1. So in this case, some of you forgot to consider 2. So 2 is my prime number, 3 is my prime number, 7 is my prime number over here. Again, perfect square are my perfect squares. 4 and 9 are my perfect squares. Sorry, wrong color. 4 and 9 are my perfect squares. Again, once you have this, if you follow the color coding, it's going to be prime numbers. I have 6 of them, so 6 over 9. Plus perfect square, 2 of them, so it's going to be 2 over 9. Answer then for 8 over 9. Answer number 1. All right, colors is your best friend when it comes to such things when it's hard to see forwards. So therefore, your highlighter it's your best friend, as quoted from one of the students I have just now. Okay, so mutually exclusive. I hope you guys got the hang of it because we still have 2 more events to go. Next one, independent events. Again, independent events, if one event, take note, the keyword here, independent, that means supposedly if one of the event happens, okay, the keyword here is this, one of the event happens, does not affect, sorry for that. The result of one event, the keyword is does not affect another event. Okay, then we then say events A and B are independent. They should not affect the answer. I mean, they should not affect each other. So one example in this case I can give is suppose tossing a coin 2 times. Okay, so does anybody want to give it a try? What is another independent event I can look for? Does anybody want to give it a shot? What is another independent event I can look for? Before I write down my answers. All right, very good. Okay, Denise, that's a good one. Drawing a card with replacement. That's a very good example. Again, take note, the card replaced should be the same card, not a different card. Otherwise, it's dependent. Okay, but then again, I got your notion. Okay, that's a very good example, Denise. Anybody else wants to try? Okay, so since Denise has said this, let me write it down. Drawing a card with replacement. Okay, take note, it should be the same card. Anybody else wants to try? Okay, so I think a little bit out of examples for that. So let me give one more. Suppose you are rolling a die 2 times. That's also one particular example that we can look at. Okay, rolling a die 2 times. Okay, now what is another weird? Before we go to the question, another rule that we can apply for independent events, it's a multiplication law. If I say both events are independent and by A and B, I can multiply them together. It's P A and B is equals to probability of A times, so A and B. You think about tossing a coin. If I'm on both heads, both of them is half, so it's going to be 1/4 half times half. That's one example that we can think of. But in general, when we talk about independent, we multiply them together. Now, as talk about coins, what is a particular example? 3 coins are tossed, one after the other. So find the probability of getting 3 tails. So in this case, how do we look at it? Probability of tails. So if we were to visualize how it looks like is this. So I have tail, tail, tail. What's the probability of getting my first tail? Half. What's the probability of getting my second tail? It's also going to be half. What's the probability of getting my third tail? It's also going to be half. So that's how my multiplication rule not only applies for 2 events, but for more, because suppose you can consider this as one event, and this is my second event, I'm just multiplying them accumulatively, which then gives me the notion of 1/8. All right, I hope this kind of makes it clearer for all of you all in terms of the multiplication of more than 2 events. In this case, we can classify one big box as one event and the other one is independent, because this whole big event on my left is independent from the single event I'm looking after. All right, so with this notion over here, all right, let's try this example again. This is not as straightforward as you think. Hint, hint, for the next bubble question, number 5. So I'm looking at the probability of getting 2 tails and 1 head. Now, is it going to be the same? Hint over here. Counting down in 3, 2, 1, let's go. Okay, so think of this carefully. Do not rush it out. Some of you are falling into the trap. Getting 2 tails and 1 head. 2 tails and 1 head. Okay, so I want 2 tails and 1 head. So what are the different ways which I can get? So 2 tails and 1 head. All right, most of you all got it. Some of you are falling into the trap over here. All right, let's count down. Last 50. Give it some time. Don't worry about it. Two tails and 1 head. What are the possible options? Last 30 seconds. Ooh, okay, doing good. I still have some of you who have yet to answer. So for those who have yet to answer, let's pick up the pace. Let's see how we can answer. All right, doing good. Last 10 seconds. Let's see. Come, let's see. Counting down to my last 10. Okay, last 5. All right. Okay, very good. Okay, most of you managed to get it. So, of course, when we talk about probabilities of 2 tails and 1 head, we all have this in mind. Half, half, and half, because each of them is half. Probability of getting a tail is half, probability of getting a head is half. But let's think about it. How many ways do I get 2 tails and 1 head in such a situation? How many possible ways? Can some of you all give me or enlighten your students, enlighten your friends over here? How many ways can I get 2 tails and 1 head for this particular option? Or in this case, how many possibilities do I have? Write it down so that everyone can share. How many possibilities can I have? Very good, Denise. That is actually all the options I have. Anybody else wants to try? In fact, Denise has given me all the options and the number as well. Anybody else wants to give it a shot? Okay, so you realize over here, we actually do have, with the help of Denise, thank you very much, 3 possibilities over here. So when I talk about 3 possibilities, okay, first one, 2 tails and 1 head configuration. I have tail, tail, head. Next one possible, I have tail, head, tail. Last one over here, I have head, tail, tail. That is another possibility. So from here, that's where you realize, oh, this one actually gives me half times half times half. But I have 3 of them. So I need to actually consider 3 groups of this possibility. And therefore, my answer is actually 3 over 8. So take note, okay, for those who have answered option 1, you only consider 1 possibility. We need to answer all possible possibilities over here, which is 3 over 8. All right, all good? Okay, I hope you guys are doing good over here, because with independent events, it's quite straightforward. But in this case, for the final revision for today's lesson, when we talk about dependent events, it's actually not so straightforward, because in this case, if I talk about if the result of one event, in this case, if it affects, you take note, the difference is not if it affects the probability of the other event. Sorry for that. The probability of the other event. We say in this case that they are dependent on each other. Okay, so what happens? Example of a particular event. Again, I used this example last week. Don't know whether you all recall. Okay, it depends on the mode of transport given the weather. Now, it may not affect this much, but suppose, let's say, given if it's raining, some of you all will prefer to take, let's say, the taxi. I'm saying example because of the walking distance you have to take from your MRT to from your home to the MRT station, say for example. Okay, given the weather. But depending on where you stay, that's where it is dependent. So this is one particular example, mode of transport given the weather. Or of course, in this case, come, let me bring it down to the floor. Any particular suggestions in this case to talk about independent event? In fact, Denise, if you just alter your sentence that you show me just now, it will actually be a dependent event already. But for the rest, I'll bring it down to the floor. Any possible suggestions for dependent event before I actually move on to another revision of the concept? Okay, so I'll just bring it down to the floor. Any particular options I have? All right, that's right. Okay, Denise, so you realize over here, if we just alter accordingly, if I have to draw cards without replacement, okay, so that means I don't replace the card, or you replace it with a different card. No, wait, does that work? Yeah, it might, but in this case, without replacement, it's actually clearer. The probability is dependent on one another. So that's one thing to take note. Now, in this case, you realize the multiplication rule doesn't really apply for dependent events. So what's another tool that we can use? This is gonna be effective, which is what we call a tree diagram. So what happens, suppose we talk about two coins are tossed, draw the tree diagram. First toss is gonna be heads and tails. Of course, you realize when we talk about this is independent events, but for dependent events, it is essentially crucial that you know your tree diagrams. So first toss, suppose this, second toss is in such a manner. So what you realize over here, for the blanks over here, we fill in the events. For the branches over here, we fill into what we call the probability, which in this case is half. Now, if I want to calculate probabilities on the branches, what is the keyword we do? What do we do along the branches? Does anybody know this particular word that we should fill in? What is the word that we should fill in over here? I'll give us something to think about it. What should we do to these branches? Do you recall that particular word? In this case, when we talk about three branches. Say, for example, I'm only looking at one tail. Okay, that's actually correct, Sophia. That's actually good. Okay, but let me bring it down to the floor. Wait for a while longer. If I were to talk about branches, if I talk this way, suppose I only want one tail, I'm talking about this way and this way. What do I do to this number on the branches over here? Okay, Sophia has given me the answer. That's a correct one. But let me bring it down to the floor. What do we do to these branches over here? The numbers on the branches, to be exact. Okay, so if you think about it, very good. Okay, start with M, U, T, we multiply. So in this case, if I were to sum all my probabilities, it's going to be half times half, or in this case, separate branches, we add that because it's either the first branch at the top or the first branch at the bottom. So we multiply. So how do we actually make use of tree diagrams? Now, in fact, questions are going to be a little bit more special over here because sometimes they may not give you in terms of words, but in terms of a diagram. So over here, how do we read this diagram? Two groups of children are selected from the group. Not two groups, sorry. Two separate children are selected from the group. Find the probability that both of them are males. Now, how do we calculate that? How do we interpret this is we need to classify into two different branches first. We want to find out males. So we group them into two parts. One is male, the other one is female. Now, can anybody tell me based on this diagram over here, my first draw, what is the probability of me getting a male over here? What is the probability of me getting a male over here? First pick of a male. If I want to pick a male, what is the probability that I have? If you have some time to think about it, what is that particular probability? Are you sure, Denise? Give it some try. How do you get the answer? Take note, sum your numbers correctly. What is my total outcomes? How many males do I have? That's the hint over here. Okay, you want to give it another shot again, Denise? That's not the answer. But good try, good try. At least you are thinking. I want you all to give it a try. So take note, how many males do I have? Or in fact, how many children do I have? Give me another try again, Chen Chen. That's actually not the answer. Okay, now let me break it down further for you. How many children are there in this particular example? Sum it all up. How many children do I have in this particular example? All right, very good, Sophia. That's actually the correct answer. But let me bring it down to the floor. Very good, Denise. We have 15 children. So out of 15 children, how many of them are male? So do you see from here how you get the probability? That's right, 6. So that's where you get the probability, because to get all the children, 6 plus 5 plus 3 plus 1, that's 15. How many males? 5 plus 1. So you have to read the correct columns and rows accordingly to get to what you want. In this case, 6 over 15. Or if we were actually to do it, we can simplify our numbers, because simplifying it actually makes things easier. 2 over 5. And female, in this case, we sum the column on the right, as indicated by my diagram over here. Okay, in this case, it's going to be 9 over 15. Over here, 3 over 5. Okay, now, from here, that's where we do our second pick. Be careful with the second pick over here, because it can get tricky. Male, female. So you have picked one male already. So how many males you have left? In this case, how do you get 2 over 15 over here, Chen Chen? I think if you're telling me the answer, it's a little bit off. We're going to try again. Because one male is gone, so that means one children is gone. My next toss is going to be 14. Take note, it's 2 over... Take note, the first one is not 2 over 3. There's no 2 over 3 over there. All right, I don't get 2 over 3. It's 2 over 5. Second one is going to be, yes, I'm going to have 5 male. That's right, Denise. And next one for the female. Female number stays the same. So it's going to be 9 over 14. All right, so be careful with replacement. You have to consider replacement. Your denominator is going to change. Okay, next up, what happens? Suppose I pick a female, so I see the change in female. It's easier to see in that manner. So what do I have over here? Okay, if I were to scroll up my tree a little bit. Yeah, I'll just zoom down my tree a little bit over here. Sorry. Okay, so let me take a look. For that, let's take a look. We simplify. Left hand and right hand. In this case, we don't have to care, Denise, because does this question talk about anything about left hand and right hand? So we have to filter the information. In fact, talking about that, your next question will focus on that, and we see how we tackle from there. All right, so male and female. Now, if you were to take a look over here, let me see how I can actually sort of... Okay, you know what? Let me draw my branches a little better so that you can zoom in to see how... zoom in to see the whole tree. Okay, so from here, suppose my male is like this. Female is like this. Yeah, it's much better. So male, female. So now my female is taken away. What happens is it's going to be a 14 down here. How many females I have left? 8. So it's going to be 8 over 14. Simplify further, I'm going to have 4 over 7. At the top, my male stays the same, 6 over 14. Therefore, I'm going to have, in this case, 3 over 7. Okay, so now I want both males. Once you have a tree diagram, it is accurate, draw my tree. So therefore, my probability, in this case, check your working over here, is not 2 over 3. That is why I meant both males. So both males, I'm going to have, in this case, 2 over 5 times 5 over 14. This simplifies, cancel my 5s, 2 over 14, henceforth leaving me with 1 over 7. So that's how I see it accordingly when I simplify. So just check your branches, just be careful when you solve. And especially, interesting question from Denise, when do we care for the left hand and right hand? We care about the left hand and right hand? Last proper question for today. Let's see how you attempt it. This one, you have to draw the tree diagram on your own. So that's why it's 2 minutes long. Take the time, make sure your tree diagram is accurate. Launching the bubble launcher in 3, 2, 1. Let's go. In fact, this is very important to see how you actually do out the tree diagram. And in fact, wow, some of y'all, I don't know how y'all did it, but y'all did it with in a few seconds. That's a good sign. But for the rest, give it a shot. How do I solve this with a tree diagram? Oh wow, you guys managed to get it very fast. Proud of y'all, good job over there. Okay, so that's where now I hope I've answered your question about whether you need to care about the left hand and right hand. This answers your question. All right, last 1 minute and 20 seconds roughly. For those who have yet to answer, pick up the pace. Let's see how we can answer them efficiently and quickly. And of course, making sure you got down the key information over there. All right. Again, this one is very specific. It's not left hand and right hand because I'm talking about a left-handed girl. So how do I classify my two branches? Very important. Okay, so over here, if I talk about the left-handed girl, I can say LHG, say for example, is my left-handed girl. And my NLFG. In this case, is my not left-handed girl. How do I solve from there? Okay, let me see. I might have missed out. Okay, I didn't miss anything. That's good. All right, simplify my last part. That is where you got the tree diagrams down. Important. Counting down to my last 15. For those of you who have to answer, give it a try. Last 10 seconds. Okay, last 3. Awesome. All right. Most of you all managed to get it, but I'll still go through because this question is rather hard. So just follow me from there. Now, left-handed girl, in this case, left-handed female. I'm actually looking at just this number over here. So knowing this number and knowing the total number of children, if I were to draw my tree diagram, okay, LFG and NLFG, if you were to refer to the legend I've drawn over here, all right, what do they represent? Okay, LFG, I have 3, so 3 over 15. NLFG, in this case, 1 over 5. NLFG, again, I were to consider, this is again, it's going to be 12 over 15. Simplify further, you realize I'm going to get 4 over 5. Now, I have to consider both cases because 2 children, so I need to draw one more branch. So in this case, LHG and non-LHG, LHG and NLHG. Again, suppose if I pick LHG, my total number of children is going to drop. Okay, it's going to drop. Okay, so what happens in this case? All right, it's going to be 14 at the denominator. How many left-handed children I have? I've picked 1, suppose. Second one is going to be 2 over 4, 1 over 7. Next up, okay, 14, my non-LHG haven't changed. Okay, non-left-handed girl hasn't changed, so it's still going to be 12. Therefore, 6 over 7. Following up at the bottom branch over here, LHG and non-left-handed girl. All right, suppose I picked a non-left-handed girl. Total number of children goes back to 14, 11 over here. Next up, left-handed girl not picked, so I still have 3 left. Okay, so that's how you fill in based on the diagrams you have. And that's why I still write it as fractions, even though it's simplified, to take note of what is the initial number over here. Easier for you to see. Now, from here, what happens? I can simplify further. In this case, I want neither a left-handed girl. From here, what we do, we trace the branches. Non-left-handed girl, non-left-handed girl. Henceforth, all I need to do is just write down my total fractions, which is none other than, okay, probability of both non-left-handed girl is going to be, in this case, 4 over 5 times 11 over 4. Simplify further, this is going to give me 22 over 45, which brings down to my answer over here. All right, so from here, what happens is this kind of questions, it brings down to how we simplify, sorry for that, brings down to how we actually simplify, how we actually simplify our, sort of like our, okay, sorry, you see a bit of, okay, how we simplify our numbers over here, which over here, the number is actually, okay, let me just cancel it out. The bunch over here is actually 1 over 7. And from there, how we identify our branches. All right, so that's how you get the answer for 2 over 35. And with that, these are all the revision that you have. And in fact, you do have a try it yourself. All right, it's actually a mock paper, which is relevant to the next week's lesson. So to give it a try, if you want to have a seamless transition to the next week's lesson, shouldn't take too long. According to teacher Kim, who set the paper, it should take about 30 minutes. So do try the questions. All right, very interesting questions get you exposed as well. Again, 60 bubbles up for grabs. So do try to get them accordingly. And yeah, that's all for today. And yes, so what have we revised? Interesting questions on sets and probability of combined events. Okay, so do let me know if there's any question and answers that I can answer for you all. If not, this is Teacher Jason signing off. I'll see you all again next week. Take care. Stay safe. All right. Bye-bye.